Good morning, and I'm Dolphy Gilpin coming to you from the Westin Atlanta, Georgia airport. It's located on Best Road, sub-number thereof at Best Road, Westin Atlanta, Georgia airport. And in previous communications, one of my mentor, CCNY, asked me what was the name of the conference, and at that time I couldn't find an appropriate name for previous meetings, but I now propose the name of the conference as the AAESSC conference. That is the AAESSC conference, and in the understanding of it is the Advanced Architectural Engineering Spectrum Communication Conference. That's the conference I propose. You might have some other one that would be more relevant, but this one I think has integrated all the ideas and thoughts that I want to express as the once more, it's the AAESSC conference. This is the conference I propose. Then once again, in previous communications, I've also found the solution of a general integral problem, an integral equation, a trigonometric integral equation, and we found a general solution thereof. And as you know, mathematics is the common language through the engineering spectrum: civil engineering, electrical engineering, mechanical engineering, civil, mechanical, structural, chemical engineering, and computer engineering. Mathematics is a common language, and therefore I have, in my commencement of this session, I try to solve it symbolically a problem mathematically, as mathematics is a common language. Later on, I'll try to do specifically some engineering problems, and once again introduce my discovery on the partial matrix determinant, the PDM, the DDLI PDM, the QDLI PDM, the PDLI PDM, the H star DLI PDM, the AO/LID PDM, and with the arithmetic progression. But I think I will leave that for the last. Things might change, but that's the way I have thought to plan this. So let's start now with the problem, the general problem solved. Mathematically, we found the solution of the integral of e to the nx cosine mx dx. And we found that in the solution to this integral problem, which is in a general form, we got now m over n squared plus m squared. I think let us do it in a systematic way. This would be n over n squared plus m squared e to the nx cosine mx plus now m over n squared plus m squared e to the nx cosine sine let's see, we have now m squared, n over n squared plus m squared e to the nx cosine mx plus m over n squared plus n squared e to the mx sine mx. And that was the general solution to the problem. And henceforth, in order to find some specific solutions, we plugged in some numbers for n and m. One of the numbers plugged in was n equals 7 and m equals 2. And that would make the problem now e to the 7x cosine 2x dx. And some of the mathematicians have solved it directly by just plugged in, giving the problem e to the 7x cosine 2x dx. And I've gone through the root and I've gotten the same answer. But I've done a general solution here now, so that we could plug in n equals 1, 2, 3, 4, 5, and m equals 1, 2, 0, 1, 2, 3, 4, 5. And we get the solution. So for this one, if we say n is equal to 7, we'll say now that the general solution for this integral problem would be now m equals 2, 2 over 7 squared plus 2 squared e 7x sine 2x. This will be plus now. I have it in a little reverse fashion here. M, which will be 7 over 7 squared plus 2 squared e to the 7x cosine 2x. And if we do this now, this would be like 2 over 53 e to the 7x sine 2x plus now 7 over 53 e to the 7x cosine 2x. And since 53 was a common factor here, we plugged it out and we got now 1 upon 53, and e to the 7x is also common, e to the 7x 2 sine 2x plus 7 cos 2x. And let's see all right, so we could in general plug in m equals some number 0, 1, 2, 3, 4, 5, and n equals number 0, 1, 2, 3, 4, 5, 6, 7, going on. And we always come up with a general a specific thing for whatever n and m we plugged in. All right, we also look at the case of plugging in a constant, say a trigonometric constant here. Suppose that we say now that n is equal to sine alpha, we sine alpha as a constant, and m is equal now to sine beta or cos beta. Where beta is also a constant. And then what we'll get here now is that the problem would turn out now to be the integral of e to the sine alpha x cosine mx where m is now equal to cos beta. So that will be equal now to e to the sine alpha x cosine cos beta x. And we take a bracket over here. There's a cosine of the whole thing, so it's cosine cos beta x. But x is a varying parameter and beta is a constant. So let us just put a little bracket around the varying parameter to differentiate from the constant parameter, which is that. And likewise, as we did this, we also got solution. And the solution therefore is like we plugged in now. This is a general form of the solution. And we plugged in now. So that would be equal now to m cos beta over n squared now sine squared n is equal to sine alpha, sine squared alpha plus now cosine squared beta e to the nx n e to the sine alpha x sine n is n over n squared plus m squared e to the nx cosine mx. So I've added the sine term. So the sine term is the second one, m, which is really cos beta first. N squared is sine alpha, m squared cos beta, e to the sine m is now equal to cos beta, x. So sine of the whole thing there. And this will be plus now n, which is sine alpha, over sine squared alpha plus cos squared beta cosine m, cosine, that is cos now, cosine beta x, the varying parameter, cosine the whole thing, and the e to the n is sine alpha x, the varying parameter. So from the general solution we have derived for this integral problem, we can plug in sine alpha, or we could recognize from sine square alpha plus cos square alpha is equal to 1. So we could simplify the expression here. Sine square alpha, so that would turn out now, this would be 1. Likewise, this would be 1. So that would be equal to e to the sine alpha x cosine beta, cosine beta x plus cosine beta over sine squared alpha plus cosine squared alpha, which is 1, e to the sine alpha x sine of the cosine of beta x. So that would be a specific solution to the general problem involving some trigonometric constant, sine alpha and cosine beta as the n and m in this case. So we have done it with trigonometric constants. We could also do it with a logarithm constant, and we plug in here now e to the n, say n is equal to say n is equal to say the logarithm of say alpha, where alpha is a constant, 1, 2, 3, or specific constant, and M equals logarithm of, say, beta, where beta is one constant again, and we plug it in here again and derive a solution to the problem. In this case, we're going to get some logarithmic parameters or expression in which we have double logarithmic. But we must remember that, like e to the ln alpha is equal to alpha. E to the ln e is equal to 1, and so e to the ln alpha would be equal to alpha. This is just for a general thing, but we're going to get a lot of logarithmic expression, and we simplify it by remembering that that is equal to that. In other words, e to the ln beta would be equal to beta. So there we have it, the general solution to this trigonometric expression, e to the nx cosine mx dx. And we plug in now trigonometric constant as well as logarithmic constant, and we could derive some solution. So that's that. We'll next move on now to some solution to certain circuit analysis now. Moving on into engineering, this is mathematics. Circuit analysis using Fourier transform and inverse Fourier transform, some circuit solutions. And I'm just going to do some basic one, but let's just take a little break here while we do the solution to the Fourier transform.